What is feedback and what are its effects? As mentioned above, the feedback can improve the system response in terms of the error signal. But this is not only effect on the system. Feedback can affect some another system performance characteristics such as stability, bandwidth, overall gain, impedance, and sensitivity. Okay, we will talk about these terms now. Feedback exists whenever there is a closed sequence of cause and effect relationships. Let's continue now. We can explain on an example. Here we have a feedback signal, feedback system. We have reference signal, output, and system gain. The output measured on feedback gain, and then in here a comparator, we will calculate the error signal. Okay. Originally, input-output relation of this system can be given as like that. How can we calculate this? Let's do this now. We have a reference signal and control system, which is represented G for this system, output, and we have a measurement, and H is feedback gain. In here, at this point, we have error signal. Okay, what is the input-output relation according to this figure? Now we can get this. M is equal to Y over R. We need this. What is the E for this block diagram? R minus Y times H. And also we can say Y is equal to E times G. Okay, this is equation 1, this is 2. When you put equation 1 into the 2, you will get Y is equal to R minus YH times G. It means RG minus GHY. GH and is equal to RG. So the relation between the output and input will be G over 1 plus GH. Okay, we can get the relation between the input and output as like that. What about the open loop system? For the open loop system, we have a reference, we have the same system, and we have output. So we can express input and output relation as G, as you see here, because Y is equal to GR. Okay, so Y over R is equal to G. As you see here, in closed loop system, we have also 1 over 1 plus GH factor. Okay, so how can we express this equation now? Let's turn to the lecture notes again. Now we have a factor of 1 plus GH, and the quantity GH may itself include a minus sign. It's not important. So the general effect of feedback is that it may increase or decrease the gain G. Imagine that if 1 plus GH greater than 1, so the total M value is less than M open loop system. Okay, M closed loop system is less than M open. So the response of the system will be changed. According to this feedback gain, the overall gain may increase or decrease. Okay, we can explain it like that. The system, open loop system, is going to closed loop. What is the changing? 1 over 1 plus GH. So, closed loop system is less than M open loop. Why? If 1 plus GH term is greater than 1. Okay. Now, overall system gain will be decrease or increase according to the 1 plus GH value. In a practical control system, it's important now. In a practical control system, both G and H value is depend on the frequency. G and H are functions of frequency. So, what does it mean? The magnitude of the 1 plus GH may be greater than 1 for one frequency range, but less than 1 in another. So what does it mean? Feedback may increase the gain of the system in one frequency range, but decrease it in another. What is the effect of the feedback on stability? What is the stability? First of all, we have to know this. If you apply a finite input to any system, the output of the system should be finite. This kind of system is named as stable. Okay, we can say about this system is stable. But if you have finite input again, but system output is infinite, so we can say about this system is instable or unstable. Okay, suppose that the last system, we can talk about this system again. You don't have feedback, and we know this system is stable. We know this system is stable. And then we apply a feedback to this system, as you see here, and assume that GH value is equal to -1. What does it mean for us? As you know, input and output relation is equal to G over 1 plus GH. We said now GH is -1. So it means the output signal will be infinite. So what does it mean for us? The nature of the system is stable, but we apply a feedback, system will go to the unstable. Okay, so it's important for us again. Let's continue. After that, we apply another feedback. As you see here, we have another feedback. The new input and output relation can be expressed with this equation. We assume that GH is equal to -1. So the system response will be G over GF, so 1 over F. If F value is selected properly, so your system will stable again. What is properly? If F is not equal to 0, your system will be stable. So feedback can improve stability or be harmful to stability. It's important. But again, I should say this, all terms such as F, H, and G is function of frequency. Okay, so the closed loop system depends on magnitude and phase of GH. I will say again, the inner loop is unstable. The system is nature stable, the outer loop or overall system, if you select F properly, again, stable. So the conclusion about this, feedback can improve stability or be harmful to stability. Another important issue is the sensitivity. What is the sensitivity? Sensitivity is a reaction about any variation to the system output. It's important in the design of a control system. Why? Because all physical elements have properties that change with environment and age. In the real world, all physical elements will change according to the time. So we cannot always consider the parameters of a control system to be completely stationary. For example, winding resistance of an electric motor change as the temperature of the motor rises during operation. Actually, winding resistance can be changed according to the temperature or motor rises during operation. So we cannot accept exactly this is stationary. So the system is sensitive to some parameters. Feedback can increase or decrease the sensitivity of a system. How? We have a mathematical equation here. This is about the sensitivity of the gain of the overall system M to the variation in G. G means actually system. System includes parameters, as you know. So the sensitivity of the gain of the overall system M to the variation in G is defined as these formulas. Okay. What is this formulas? Percentage change in M, percentage change in G. But in here, it should be M and it should be G. Yes, if you evaluate this formula, you will get this. Maybe we can do this now. We have this formula for the sensitivity. And we know this. M is equal to G over 1 plus GH for the closed loop system, feedback system. Okay. Sensitivity M according to the G, partial differential M over partial differential G. So we can edit this equation as like that. Partial differential M to G times G over M. Let's get this now from this equation. Partial differential according to the G, 1 times 1 plus GH minus G times H over 1 plus GH square. This term cancelled to each other, so it will be 1 over 1 plus GH square. Let's put in here this expression. SGM is equal to 1 over 1 plus GH square times G, as you see here, over M. Where is M? Here. G over 1 plus GH. So some terms will cancel to each other as like that and as like that. It will be now 1 over 1 plus GH. Let's turn to the lecture notes. Yes, as you see here, the sensitivity function can be obtained as like that. What does it mean? This relation shows that if GH is a positive constant. What does it mean? The magnitude of the sensitivity function can be made arbitrarily small by increasing GH, provided that the system remains stable. What are we talking about? If this expression is small, as small possible as small, so it means the overall system is insensitive to the parameter variation. Okay, we always want this. The control system should insensitive to the parameter variations. What about the open loop system? If your system is open loop, what will be happen? Open loop system, y over r or m is equal to g. So the sensitivity OM according to G will be M G G M. So the partial equation will be 1 and times with G and M again can be put here. Sorry, G. It will be 1. What does it mean for us? The parameter variations directly affect to the system response, but we don't want it. Okay, we don't want it. The sensitivity should be lesser as possible as. Okay, let's continue. Effect of feedback on external disturbance or noise. It's a conclusion. Feedback can reduce the effect of noise. What is noise? Every physical system, some noise. For example, in here, maybe we have some examples. Yes. Example of the signals are thermal noise voltage in electronic circuit and brush or commutator noise in electric motors. Okay. For every system, we know this, we have some noise. And we want again, the system is insensitive to the noise signal to control operation. These represent the noise for the system. We have G1, G2, and H, as you see. Imagine that H is 0. The system will be open loop. Only evaluate the noise, not reference. Reference should be 0. So the system output will be G2 to times N, as in this equation. But if you have a feedback, what will be happen now? Your new system will be as like that. What is the difference between them? As you see here, we have a factor of 1 over 1 plus G1, G2, H. Okay, if this value is greater than 1, it means the system is insensitive to the noise. Okay. Originally, we want this. So the feedback can, feedback can reduce the effect of noise. But we know this again. I should also say this. All gain is function of the frequency, so it's also evaluate. Yes, the other effect of the feedback is bandwidth, impedance, transient responses, and frequency responses. All effect will be explained as we continue. But now, for now, we know this feedback. We learned overall gain effect, stability, sensitivity, and also noise or disturbances.